So this is going to be our chapter on musical sounds. While there is not a ton of science to this or a ton of hugely important works that can be done with this, so you can't make a dam, you can't make a transistor out this. It is very important in understanding the ideal that all of these functions, all of these different types of sounds that are coming out of us are a combination of sinusoidal waves. The first thing that I'm going to talk about that isn't very much related to musical sound is just our understanding of intensity. So, intensity is measured using decibels, where each decibel, every 10 decibels, is going to be 10 times greater than the previous 10 decibels. So a 20 decibel sound is 10 times greater than a 10 decibel sound and 100 times greater than a 0 decibel sound. The reason that this is a logarithmic scale instead of a linear scale is that we tend to perceive sounds by how much bigger they are than other sounds multiplied by how much bigger they are than other sounds, not adding how much bigger they are than other sounds. So we perceive about the same distance between 110 and 120 decibels as we do between about 10 and 20 decibels, even though 120 decibels has an intensity of 1 watt per meter squared, and 20 decibel only has an intensity of 10 to the negative 10 watt per meter squared, or about 10 billion times less intensity than the intensity that we get from the 120 decibel sound, the air raid siren versus the whisper. Now, talking about music instead, most musical sounds are a superposition of many tones that differ in frequency. The various tones are called partial tones, are simply partials. The lowest frequency, called the fundamental frequency, determines the pitch of the note. Partial tone whose frequency is a whole numbered multiple of the fundamental frequencies is called a harmonic. Different harmonics have different pitches. A tone that has twice the frequency of the fundamental is the second harmonic. A tone with three times the frequency is the third harmonic, and so on. It is the variety of partial tones that give a musical note its characteristic qualities. So we see that musical instruments have characteristic timbres. Each has its own color. For example, what you're seeing is that if I pull out a guitar, which, by the way, I don't actually know how to use, I just know very basic physics about it. You have the first harmonic, which is going to be the a wavelength from the top of the guitar, from the neck of the guitar to the base of the guitar. It's going to have that same wavelength as the string. The second harmonic is going to be the second wavelength that can create standing waves, and then the third harmonic is going to be the third wavelength, and the fourth harmonic is going to be the fourth wavelength. So when you add them all together, instead of just having a pure sinusoidal tone, what you're going to end up having is a composite wave that looks like a combination of the three harmonics. We also have standing waves in something like pipes. So for a pipe organ, which I believe is an open pipe, instead of having a standing wave which is cut off at the ends at a node, it is cut off at an antinode, and those allow the standing waves which are allowed. And then if you have a flute, which is a pipe that's closed off on one end, then you have one end which is going to be a node and one end which is going to be an antinode, allowing different standing waves. What I found was a microphone sound analyzer, which tells you both the waveform that is going to come out of the microphone and the frequencies that make up the waves that compose it. So this analysis of the frequencies that make up the waves that compose a more complex waveform is called Fourier analysis. So if we look at our guitar, I am going to play a note which is called an E note. That is going to be a note where the first string is just left completely open. So the length of the string is going to be the wavelength of the fundamental harmonic. You see that you have a high first harmonic, a high second harmonic, or a high fundamental, a high second harmonic, and a high third harmonic, and a smaller fourth harmonic, uh, and just these different combinations of the waves. But if I go halfway down the guitar and play a string that is half as long, then that is going to mean that the fundamental harmonic is going to be twice as high. You'll see that instead of you'll see that instead of repeating every 0.33 kilohertz, it repeats every 0.66 kilohertz. This note, which has half as much wavelength, is still called the same note. It's just up an octave. The next most complicated thing in music is a chord, which is a combination of different notes played together at the same time. So in this case, if you look at the frequencies, you'll see that periodic spikes, except it's going to be periodic spikes of all of the different notes which are made up. Looking at my voice, you see that it's a lot closer to white noise than the sound of the guitar, even though the vocal cords are controlled by similar methods. And looking at any sort of sound, you are going to see that the wave is always this combination of sine waves. And it turns out that any sort of function whatsoever can be thought of as a combination of different sine waves with different intensities.